Our penultimate speaker this year is no stranger to this event, Kathy Ehrig. I think it's Kathy's continuing our eternal learnings on the Olympic dam system, for which we're all grateful. So without any further introduction, I'll hand over to Kathy.
Thank you. I need to go to full screen on the monitor. I don't have a chance in hell of reading that. Thank you always for Nicole and Jeanette to continue to invite me to present here. Today we're going to talk a little bit about the Olympic Dam Deeps. There was a public release for it, as people probably know, back in January of this year. It's a new mineralized area, and it's important to know that our 50th anniversary of the discovery of Olympic Dam is coming up in July of 2005. So still after all this time, we're still finding or defining newer areas of mineralization. That picture, that drill core is, it's in Q, so 50 mil up and down, and it's just got nice chalcopyrite in it. Chalcopyrite, pyrite in the hematite breccia at about 2,000 meters depth. The old standard disclaimer, acknowledgements. Anything that I present here is based on my opinion, but it's based on a lot of work that a lot of other people done. And we always need to recognize that people have gone before us. And the Olympic Dam, there's been over 200 geoscientists that have worked on the deposit since discovery in 1975. Some of the stuff that's presented today is not the work that I've done on doing the drilling and all of the other hard work. I just got to sit on the side and look more at the science side of it. But the special acknowledgement go out to the Deeps team. We're heavily focused for several years. BHP Innovation and BHP Resource Center of Excellence. But over a long time ago, and it's important that because of Paul Hethersay going to be the ultimate speaker here, the ultimate one at the end of the day, is to recognize the importance of the South Australian government and the leadership that Paul Hethersay has provided really on my personal benefit on the geology side. And Olympic Dam, we have published over 200 papers on the geology and the geomet of the deposit since about 2013. And a lot of that has had to do with Paul's influence on frankly, on BHP and the local side of it, so it can't be underplayed. A lot of different collaborators in there. We've gone out and worked with universities and worked with different government agencies and all that, and we continue to get support from the Australian Research Council. The Olympic Dam Deeps, extensive mineralization and mineralization continuity. It was publicly released in January 2024, but the best thing for us is being on the front page of that, and the front page for good reasons, not for bad reasons of the CEO's public release. And there's that quote there, we have undertaken 62 kilometers of exploratory drilling beneath the deposit, which has shown extensive mineralization continuity with attractive copper grades of above 1% along a strike length of more than 2 kilometers and greater than 1 kilometer depth. So we'll go on. Now, before I jump into it, there's a lot of drill core out on display. And this is mainly around the deeps areas. There is some shallower parts of the deposit, but there's also a lot more cross sections in there in more detail than what I'm going on in here. So first of all, we'll look at the picture of the deposit. And I'm sorry, I'm going to have to turn my back a little bit on you. Over here, the typical thing, fresh Roxby Downs granite. It's all not fresh, but mostly fresh, or there's pockets of fresh in there. An outline of really where the breccia complex starts, and that's where you start getting reasonable amounts of brecciation in the rock, but really where the iron content starts to go progressively above 5%. Also in here, that these shades of gray, which are really just the increase in the amount of iron oxide going in the deposit and some bedded clastic facies. But the whole area around the deeps, what's going to be the deeps, we'll talk about it here. The important thing was several years ago, we actually recognized that alteration halo that we see up here just didn't occur here, down in this part of the deposit. And I'm going to focus in on that, and I'm going to focus in this gray area in here. We want to go back and look and say, how good is this? This has evolved a lot with time. My predecessors actually did a very, very good job on defining that outer envelope. And And in a more modern sense, we actually have a Fourier-derived vertical gravity gradient image of the breccia complex. So I'm going to obviously have to change this outline. I think this is pretty good. And this classic shape here, and that shape there is really very roughly our resource outline, and that's kind of tracking along in that orange there. Important things to note: RD1, the discovery hole; RD10 was the true discovery hole; 2773, which was the deepest hole in the deposit until about 2 years ago, and I drilled that one. I didn't drill the new one. RD 1980, we're going to focus on this and look around that deeps area a little bit. So the deeps, I have to look down here and read for a minute. We often forget, and as we become more modern and more of these things are at our fingertips all the time, we actually think the world just evolves here in 5 minutes. Every 5 minutes, the world's turning over. And we are developing more of a habit of actually not understanding what's gone before us. And what's gone before us is things like the ideas and outcomes of, that might have happened a decade ago or 15 years ago, or even further out in the deposit. So it's really important that we understand the value of going through a lot of the old data that it's available and becoming even more readily available. So much on the soapbox. 2003, 2005, and Roy Woodall always constantly hassled me about where's the feeder zone to this deposit. And you need to drill a hole down the feeder zone. Well, we didn't even have a clue where it was. But we were asking at that time, what does the deposit, what does geophysics actually tell us below the level of drilling at that time? Because WMC was in the point of, they were doing a lot of extra drilling, and they were in sellout mode. Based on gravity inversions, we made a missing mass model, and that missing mass model took that gravity data and all of the bulk dry density measurements that we do on all of our drill core samples anyway, and came out where there was some big gaps. And that big gap actually happened to be in that area, around that area that's marked by 1988. So the geologist, a hole went down it. And in RD 1988, and that hole was drilled in 2006, and it ended at 1897 meters. But what was more important is it ended in 1.6% copper, 1.2 grams per ton of gold, and there was some uranium and silver went along with it. And it turned out to have very distinctive geochemical anomaly. So because we're in a vertically oriented ore body with a vertical hole, you'd say, well, that's a bit dodgy. Yes, we did 2 directional drilling holes at that time that were actually designed to go down around 1,800 meters, 1,500 or 1,800 meters, to see what the real thickness of that zone actually might be. And each of those holes had a width of mineralization down at that depth, between 130 to 180 meters. But at that time, the open pit expansion work was going on, and that kind of depth was very deep for a metals mine deposit, excluding the gold, particularly back in the day, 2006, 2007. But it was actually never forgotten, but was put in a low priority category because you know what? We had 8, 9, 10 billion tons of material that's accessible at more than 1,000 meters shallower than where this stuff existed. So never forgotten, just waiting for opportunity. Now, the model that was developed then, but then modified as we moved, started to progress in the underground operations from the northern mine area into the southern mine area, is represented by this cross-section here, the pseudo cross-section. RD 1988 kind of goes down the gut of it. One of the directional drilling holes come down here, and to measure what the thickness of mineralization was. And that's very cool, believe me, very cool. And because of that, I remained fascinated as to what was happening out in this area, and then particularly this transition when we go from the edges of the mineralization, of which we only hit a couple spots of it, and see what happens over this very short area when we go into fresh rock Sweet Downs granite. Now, just a few geochemical profiles. So we're going left to right, and copper going down, and there really wasn't much copper, nothing economic, nothing above 1% until you're down about 900 meters, and it just continues as you go down the profile. Mag sus has continued to ramp up, but not very high. Bulk dry density We know it was very iron rich, so you see that bulk dry density between 3.5 and 4, which in hematite all the way, or iron oxides all the way. And then looking at simple things like potassium alumina ratio gives us an idea whether we're in a sericite K feldspar dominated area when you have the values really greater than about 0.5. Or areas that are more sericite chlorite rich. And you can see that we were hitting pockets of sericite, more sericite K feldspar out there. It's a very good alteration indicator. We're going to flick on and flick up all kinds of other elements on here. So looking at the copper profile again and keeping that idea of about 900 meters depth, because the stuff shallower we would have encountered it elsewhere in the deposit. Gold being really good grade all the way down. Barium as barite, relatively high for the deposit. So a typical deposit value for barite or barium is around 2%. And this area actually had a lot of it. And so it turns out it's a later stage overprint. But more interesting was the moly. And we can see red lines, very thin red lines for moly, antimony, arsenic, and you can do the same for tin and tungsten. And the red lines represent off of these diagrams what a more of a typical ore body one is for Olympic Dam. And you can see very enriched in moly. That was going to be my fifth revenue element there, that I was going to become a champion, but we could never recover it for a whole variety of different reasons. Antimony and arsenic. So we can see that there was a different geochemical signature down there. Now, a long time ago, open pit time was over. We go more into expanding, really getting the northern mine area and working on expansion into the southern mine area to continue on the operation. So we're going to go fast forward from 2007 up to about 2020. But this picture here is from another one of those two directional drilling holes that went down. And this is about 2,000 meters where there's nice chalcopyrite and pyrite inside of with hematite and sericite quartz. Again, back to the old, the image that we're going to see a lot more frequently in here. And the first of all is the area of the deeps drilling, which is this big box here. And this is part of the public release. So the drilling that occurred between November 21 to September 23, and that's about that 62 kilometers of drilling. And the purpose of that drilling was not to find material at 800 or 900 meters depth. It was really targeting 12 to 1,500 meters and more. It was part of big window of opportunity open to understand what a long-term growth opportunity would be for Olympic Dam after we deplete that shallower 10 billion tons. The image on the right-hand side shows the outline of the resource outline, and all the gray, the gray just represents a projection of all the drill holes that I've ever done in the deposit, and these darker lines are representing what the deeps drilling was doing, or shows where they're really focused on. And again, a long ways off because of targeting down at roughly 1,500 meters, and wanting to come in at relatively shallow angles so we get a better control on mineralization. So that allowed us to actually step out from the deposit, particularly to the south. For me, it was excellent because I could see something in an area that I wanted to study a lot more. Well, we're going to look at kind of two sections here. There were a couple of them published in the public release, another one there, but we're going to look along this one and then just another one a little bit further out. See where I am with the time. Now, the important thing off of here, this is a leapfrog model, but the leapfrog model on here, so this is where we can see this fan coming down here, and the depth, I'm sorry, I forgot to put this in higher. That's minus 1,500 meters, that's 2,000, so they're 500-meter blocks going in here, and a fan of holes, with 3 holes coming down, and intentionally going across the zone of mineralization, or what we thought was mineralization, and that's clearly in there. And this is all the other shallow drilling that occurred. This drill hole here is an important one. It's RD4597. It's now the deepest hole in the deposit, and you can see it goes down to well below 2 kilometers depth. The important lines on here, the modeling team and the geologists that were doing the logging, this is where the Woodall Fault is, which is kind of our boundary between rocks that have fresh Roxby Downs granite and then ones that actually don't have fresh Roxby Downs granite anymore. Clearly a bounding fault, which we call the Woodall Fault, Woodall Junior Fault, to that deep mineralization, but really focused in here. So we won't worry about that rest of that area. Now, things that you're going to see for the not quite yet, I jumped myself, for the very first time, but not yet. Downhole profiles off of these. The mag-sus, and when we see mag-sus in times 10 to the minus 3 SI units, values of 10 are 0.3% magnetite. And so at 10, it's 0.3% magnetite, very roughly, 0.3 volume percent magnetite, and 100 is 3%. We can see quite a bit of change in those, and usually as we start going deeper, we'll pick up more magnetite. You go down, you can just look at the density, potassium aluminum ratio, silica, but more importantly, again, is the copper, what that copper is doing. And we'll flip up here. This is kind of the shallower part of the deposit, so no prizes for that, but more of these zones down deeper, and as we cross-cut that deep zone of deep mineralization. And then you go off and you get little spikes. This is all in granite land, but there's a lot of little spikes in copper and all kinds of other things. Our classic arsenic, these areas as we go deeper are more carbonate rich, so magnetite, carbonate, pyrite, chalcopyrite is the norm down there, and even little kicks in the cerium and all the rare earths. So we'll just continue on. So I think now is it. Now, this is a part of our 3D seismic work that's been done over the last couple of years at Olympic Dam. We started off with a sparse survey to learn a lot, and then there's just been a full bang of running a full 3D survey. A year and a half ago, I'm trying to think, maybe even 2 years ago, my time frame's messed up a little bit. The processing of this size of a full 3D geophysical or a seismic process is no mean feat. We know that the processing actually takes far longer than what the data acquisition. Data acquisition's easy once you get all the parameters right, but that processing. This image is where we see RD4597, so it's that same cross-section we were looking at before. Down the vertical axis is 1,000 meters, 2,000, and it bottoms at almost 8,000 meters below the surface. And this is not the final image. This is just one that was generated back during the early processing of this back in May of this year. The important things to point out on here, and these are always cool, base of Roxby Downs granite. Now, we kind of knew this from the Geoscience Australia Global Cratonal Transects back in the early 2000s. We have this idea from MT work, the very regional M work, but it's also nice to see it around Olympic Dam. The really cool thing, though, here is you see this, the mineralization and everything up here, but this real wrinkle or a lot of extra reflectivity going on here. And this, we'll show you another image later on, actually tells it that Olympic Dam doesn't bottom down there. Does sulfide mineralization more than likely, not too far below our drilling, but it still shows that Olympic Dam's big, and there's conduits that are coming up from depth that are actually part of this system. The other stuff that we see, and so much more to do, and Dave Haddo and Matt Goldman right now with support from others and the RCOE are now starting to go after the geological interps, but out in the Roxby Downs granite, you see these big reflectors here. The edge of the deeps, this is clearly marked along that zone, but there's so much texture to work out and to work out for a long time to come. Eventually, all of the data will be made public, but we still need a time to play with this information. So that in itself, when I saw that's like, this is beautiful, and when it's even processed and refined even more, we'll just learn more about the main, number one, the architecture of the deposit. But let's flip forward. Now I'm going to go about 800 meters to the east, and looking on the edge where there's another drill hole, which was called RD4594, and that happened to be in the deeps drilling, the furthest extent east that the deeps drilling actually went. And we look at this feature again. It's the same vertical scale and horizontal scale. And what do we see? Base of Roxby Downs granite. And I have Wallaroo metasediments. People like the Hutchinson group, but I like the Wallaroo metasediments a little bit more, and that's just a personal bias. We see these low angle or relatively low angle features out there. Who knows what that really is? And we're not likely to drill into that for a long time to come. But then you start seeing the effects off of here a little bit more of the Gardner Dyke swarm, which the Gardner Dyke swarm does cut across the whole deposit. Again, and then you look in here, well, this is pretty well developed, and this RD4594, it ended When it ended, it had just started going into Gardner Dike swarm. And I think if Dave Haddo at the time would have had this information, this detailed information, it might have gone on a lot further. But still, at that kind of depth, that's really pushing everything, particularly because all the real mineralization's up higher. But we see this strong feature, and then you say, well, you know, we know there's a lot of Gardner dikes around. We know there's a lot of there's 1590 mafic and ultramafics around there. And given that there was just the hole just happened to end in Gardner dolerites, could this just be a bigger dolerite blob? We don't know. Now, continue on. So this, there's a lot of focus will be up in the shallower parts of the deposit. Let me just jump up here a little bit. The base of the cover sequence, which is about 350 meters underneath the deposit, this is what all that sub-parallel reflectors are doing. And then once we're in the really guts of the deposit up in this area. But again, this is just I wanted the team actually produced this for me on Tuesday because they got the full 3D cube just on Monday, I think, late on Monday. But I wanted the bigger picture. They're obviously going to be focused down in that area, okay? Now, so what I've done is taken that first cross section and we're just going to skimp this side of it. And we reflect back, and I didn't show the Geoscience Australia seismic line that went across there a long time. This is a gravity and magnetic inversion back from 2005, and there were less refined ones during WMC time before that. And when I first started Olympic Dam, you know, everything, you know, there's a lot of stuff at 10 kilometers depth underneath Olympic Dam. When I used to say, well, and reference to my lovely colleague Jim Hannison in the back, when I hear a typical geophysical response, the depth of whatever you're looking for is 10 kilometers, I said, well, that's nonsense. You know, this case, it probably turned out to be true, but that seemed to be a common kind of thing, the depths. But we know how difficult it is to get all this stuff right. The beauty, sorry, can you just go, no, I can do it. The beauty off of this is even back then and even during WMC time, they knew that there was this long column. No matter what they did to the gravity and magnetic still suggested that, and that data continues to show. So we'll jump around a little bit. Now, this is up to near the conclusion here. The deeps drilling from the discoveries, insights, and conclusions. The deeps drilling program was completed in June 2024, and it achieved the objectives of that program plus a lot more. And all of you smart explorers out there on the BHP's release, if I was out exploring, I would have digitized all that, and you could come out with a rough tons estimate from that 2 kilometers of strike length where the mineralization is added, and it's very, very significant as far as tons addition at greater than 1% copper. But in addition to that, we also learned more about the architecture of the deposit. So the mineralization at Olympic Dam actually remains open at depth, not across the whole deposit, but in that southern mine area or off on the southeastern margin of that deposit. The overall program did about 132 kilometers of drilling, roughly 94 from the surface, and about 38 kilometers from underground platforms. So you say at that depth, why were we drilling both from underground platforms and up at the surface? Underground platforms would have been the best thing, but because the areas where we needed to drill from to reach those deeper areas of mineralizations at the angles that we wanted to hit it, a lot of the platforms would have taken several years to get the development out to those areas and those platforms developed. But Dave Haddo was very astute at that time, who was doing all the drill planning early on, and noticed that there were platforms available. So that actually gave us hits from both directions. The deeps, though, is not a separate deposit. It's a continuation of the deposit that sits right above it. The top of the deeps, there's nothing magic about it, but it's really demarked by the shallow, it's demarked by the old resource outline. You know, you might say the bottom of, but it was really where the base of all the old drilling was. So it's kind of a real loose term. The Woodall Junior Fault clearly is the southern bounding to that fault zone, is the bounding fault on the southern margin within that area of the deepest mineralization. The Woodall Fault, which sits about 250 meters to the further south of that, clearly separates fresh Roxby Downs granite, or areas we have fresh Roxby Downs granite, from granite that is becoming more and more altered. But the cool thing in that area, of which we've touched on a couple presentations, and when you look at some of those pieces of drill core, that we see abundant granophyric textures, we see abundant quartz tourmaline, quartz carbonate dikes, and some even late carbonate pyrite, chalcopyrite veins too that cross-cut most everything else. There's pegmatitic blob, there's apatite, and those apatites clearly have granophyric texture to them. There's a whole wealth of information there that we believe that they're analogous, and this is always loose because this come out of the porphyry world, from crystal mush dikes, but really fluid pathways, mega opened up fluid pathways. The big thing to look forward to is the OD3D seismic data. The processing has taken a while to go through, and there will be future generations of processing that data, but the team actually had to start going with Geological and TERPs, and they're well on to their way, so I'd expect next year, if Jeanette invites us again, or Nicole and Jeanette, that they'll be talking more about the outcomes of that. The piece of drill core on the far right-hand side is just the from 4597 down at about 25, 85 meters below the surface. And what we can see, we see pyrite in there. There's a lot of hematite, magnetite, and little fragments of granites in there. This here, that's a 1 inch block. And this 1 inch block where we've just done automated mineralogy across it. Yellow is pyrite. The pinks are, the tans are chalcopyrite. That blue is apatite, that darker blue. The green is hematite. The brown is quartz. The bluish, that pale blue or kind of sea green color is sericite, and the pink is K-feldspars. But the big thing here, we look down and there's hematite, magnetite, roughly 24% quartz, sericite, K-feldspar, apatite, pyrite, chalcopyrite, monazite, but trace amounts of bastnasite, crandallite, centrosite, molybdenite, rutyl chlorite, anhydrite, this goes on and on, barite, fluorite, tourmaline, siderite, calcite, branorite, and thorite. It's still open, all the mineralizations around, though it's getting narrower. So that's actually all I have to say, but again, I'd like to acknowledge Paul Heathersay and his support in the background for us getting out and publishing this plus 200 publications that have come out since starting at about 2010 and going on from there. And without Paul, I would say that I would have published, but it would have been nowhere that amount of effort that's gone into it. So thank you.